In the case of continuous time harmonically related complex exponential signals, we know that we have e power j omega 0 t, and when the values of omega 0 varies from 0 to infinity, we can have an infinite number of harmonically related complex exponentials. However, that is not the case of a discrete time harmonically related complex exponentials. If we take the signal e power j omega n, we can see that there are only a finite number of harmonically related complex exponential exist within the range 0 to 2 pi in frequency, and after that you can see that the same complex exponentials are repeating. So we can see that identical signals exist every 2 pi interval of frequency in the case of discrete time harmonically related complex exponentials. That is the main reason why the DTFS series is a finite series. So let us understand more about that in this video.
Consider our discrete time complex exponential signal e power j omega 0 n. Instead of the fundamental frequency omega 0, just substitute omega 0 plus 2 pi. Now we can expand it like this. E power j omega 0 plus 2 pi n is equal to e power j omega 0 n into e power j 2 pi n. From this equation we can see that n take only integer values. Hence e power j 2 pi n will be always equal to 1. Thus we will get e power j omega 0 plus 2 pi n is equal to e power j omega 0 n into e power j 2 pi n is equal to e power j omega 0 n. From this equation we can conclude that the discrete time exponential at a frequency omega 0 plus 2 pi is exactly similar to the discrete time complex exponential at a frequency omega 0. Thus we have a very different situation from the continuous time case here. In the case of continuous time, the signal e power j omega 0 t are all distinct signals for different values of omega 0, and omega 0 can take any values from 0 to infinity. They are all different signals. So different harmonically related periodic signals. In the discrete time case, these signals are not distinct. Here we can see that the signal with fundamental frequency omega 0 is identical to the signal with fundamental frequency omega 0 plus or minus 2 pi, omega 0 plus or minus 4 pi, omega 0 plus or minus 6 pi, so on. Because when we substitute these values 2 pi, 4 pi, 6 pi into the equation e power j omega 0 n, we can get the same e power j omega 0 n as the result. Therefore, in considering discrete time complex exponential signal, we need to consider only a frequency interval of 2 pi in which we have to choose the omega 0. This interval can be 0 to 2 pi or minus pi to pi, which we have already discussed in elementary signals. Now consider our harmonically related complex exponential phi k of n, which is equal to e power j 2 pi by n into n, which we have already discussed in the previous video, where k can take different values like 0, plus or minus 1, plus or minus 2, plus or minus 3, like that. Now compute phi k plus n of n, which can be computed as e power j. Instead of k we have to substitute k plus n, so e power j k plus n 2 pi by n into n. Now if you expand this, you will get like e power jk 2 pi by n into n, and the next term is e power j 2 pi by n into n, which will give us e power j 2 pi n. Now in this equation we can say that again n can take only integer values, so e power j 2 pi n will be always equal to 1, and finally we will get the result as e power jk 2 pi by n into n, which is equal to the actual signal phi k of n, that is phi of k plus n n is equal to phi k of n. So this equation proves that there are only n distinct harmonically related periodic complex exponential signals exist in the case of discrete time signals. These distinct harmonically related periodic exponential signals are phi 0 of n, which is equal to 1, phi 1 of n, which is e power j 2 pi by n into n, and phi 2 of n, which is e power j 4 pi by n into n, and etc. up to phi n minus 1 of n, which is equal to e power j 2 into n minus 1 pi by n into n. Any other phi k of n is identical to this above harmonically related periodic exponentials. Thus we can say that phi 0 of n will be equal to phi n of n, because we have only n distinct harmonically related complex exponential, which is again equal to phi 2n of n, and similarly phi 1 of n will be equal to phi n plus 1 of n, which is equal to phi 2n plus 1 of n, because we can have only n distinct harmonically related complex exponential. So this will continue. So generally we can write phi k of n is equal to phi k plus Rn of n. This equation says that when k is changed by an integer multiple of capital N, that is an integer multiple of the total number of samples, the identical sequences are generated. Harmonically related complex exponentials will not keep on going. Instead we will have only n distinct harmonically related complex exponentials. When we change the k value by an integer multiple of n, that is n, 3n or 4n, like that, we will get the same signals again and again. That means that the fundamental frequency is equal to the nth harmonic, and the first harmonic, that is phi 1 of n, is equal to n plus 1th harmonic, and so on. That means we have only n distinct harmonics in the range minus pi to pi in the case of discrete time complex exponential signal. So this is a very important result, which is very different from the continuous time case. So two things we have summarized here. One is harmonically related complex exponential exists only within the range 0 to 2 pi, or after that it will repeat. And the second point is that these harmonically related complex exponentials are finite. We have only n distinct harmonically related complex exponentials within the range 0 to 2 pi or minus pi to pi, which is entirely different from the case of continuous time case.
I hope you got a clear idea why there are only a finite number of harmonically related complex exponential in the case of discrete time complex exponentials. This concept is very important to understand the nature of DTFS.